So today's lecture 4, I want to cover more advanced optimization for linear regression. And so this where we are still in supervised regression and tabular data. And from this nutshell view, today we already finished like everything about linear regression. Today we just focus on optimization using gradient descent and stochastic gradient descent. And so if you remember, like in the lecture 1 and 2, I did not touch anything about optimization, not much. It's just because I leave it to today to tell you a little bit more about more details. Okay, so before I step into the gradient descent, I want to just lay out this a little bit more general concept called optimization. So what do I even mean optimization? So we can use this general definitions, kind of guide us in later. So the optimization has objective function, like we can just denote it as fx. We can also denote it as j theta. It's all just notation. And for this objective function, you have a variable to search. And your objective is mostly either to minimize or to maximize this objective function and to look for that specific value of this x variable, or in the j theta case, the theta variable, that minimize or maximize the objective function. So because they just, it's a minus relationships, right? So we normally just focus on minimization, because for the maximization, you can just minimize the minors of that function. And in a lot of cases, you also have constraints. So what we covered so far, there are no constraints. But I think from the maybe the next class, I will have optimization. There are constraints to consider. Okay, so let's put our normal equation-based solution in this optimization formulation. So in fact, the normal equation based, or that gradient set gradient equal to 0 based, you can think about that kind of approach is to directly optimize the objective function. So let's review this specific example we actually showed you. It's just super simple. It's this loss function that's only W1 W parameter to look for. And it's a quadratic, which is a U-shaped function. And actually U-shape, there's really the minimum point is this center of that U, right? So we actually just reviewed, super easy. We can calculate the derivative of this W function, and we get its derivative as 2W. Then we just set it to 0, that derivative to 0, that give me the best W star. And so the reason why we can directly optimize by just looking for that W satisfy this constraint, because this is a convex function. And we can find zeros for this type of convex function just by this satisfy this constraints, because there's the convex function. Those derivative 0 points are the minimum point. It's just guaranteed by the properties. And also, so then we use the same procedure to solve our linear regression training. And we actually showed you what's the cost function look like. And then it's really just a summation of the square error over all the training data. And then we did some kind of derivation and to put it into matrix vector form, like to use the BLAST library easier. And then we set it to 0, and this gives us this normal equation based formulation, which is here. Then actually you normally give this just to the solver, and the linear, those kind of linear equation solver can just solve it. But because in our implementation, we're going to use this to implement, because it just to give you a direct view of how the solution looks like. But there are actually a lot of details how to implement this normal equation. But we will leave that as extra content if you are interested. I have some extra slides how to solve this. Okay, so as I told you, I mean, the reason why we can use this set it to 0 and then solve it, because this is a convex function, right? It's actually easy to solve. And in the previous case, that quadratic case. So how could I guarantee this is a convex function too? How could I guarantee that the j theta is a convex function? So there's some kind of, there are some more mathematical details I actually left out, but I want to do it really quickly here for those of you who want to learn more. So we can actually calculate the j theta's Hessian matrix, and this Hessian matrix is related to x transposition x, and this x transposition x, it's normally called Gram matrix. And Gram matrix are in general positive semi-definite. So when the Hessian of a function is positive semi-definite, this function is convex. And it's actually very simple for us, just directly set it to 0, and then we get the solution is unique. And that gives us a unique solution, theta star. So if you do not understand it, that's okay. But I want to still introduce a bit for those students who wanted to learn more. All right, so this is a good function. So j theta, that square sum of squared area is really a good function. And there's a reason why we introduce it first, because it's really a function, easy to take gradient, it's easy to do differentiation, and also has good properties. Okay, so then I give you this detailed 3 points, like hand solve it. So then I solve it through this Gaussian elimination method, which I only include 2 points there, because if I have had more points, like this equation could be even longer, and then it's a little cost time. But anyway, so this shows you this Gaussian elimination-based solution just on a concrete example. Okay, so you're going to implement that solution as the first part of the homework programming, which is actually super easy, right? You already tell. I mean, it's really just you learn a little bit about NumPy, and then you just write out x transposition x, then take inverse, then times x transposition y. That's it. Okay, so now let's shift to a much more general like observation method. Instead of directly solve it and then requires the function to be very, very good, has very good properties. If the majority of the cases, our loss function are not that nicely behaved. And this, there's a group of methods called gradient descent. The gradient descent method is, okay, so instead of directly looking for to set that gradient equal to 0, in many cases, you just can't solve it. We have good cases you can directly solve it, but the majority of the functions, loss functions are very complex. You can solve it. And also, yeah, you just can't solve it. So if you can't directly solve that gradient, set gradient f versus x equal to 0, how do you minimize f function? And this is the method to use. It's really the state of the art people use now, called gradient descent. So rather than directly guess the best solution, I try to start from some random starting x0, then I keep updating that previous xk plus k minus 1. So I start from x0, I update x0 into x1, and then x1 into x2, onto x3, and just keep updating and until kind of converge. And I will tell you what do I mean convergence in later slides, but you can just, yeah, it converges to this point that minimized f function. And this xk minus 1 to xk, it just follows really odd, weird looking function. It's xk equals xk minus 1 minus a alpha. Alpha is called, it's actually a hyperparameter, user defined. And this is called learning rate. It's defined by the designer, defined by the user. So it's given. You can think about this alpha, it's given. And then I multiply this alpha by the gradient of my function at that xk minus 1 point. And okay, so we normally call, this is called kth epoch update. And we're updating many epochs, maybe like onto xt epochs, like epoch 0 onto epoch t. All right, so why this makes sense? So before I jump details into the algorithm, let's review a little bit about what's the definition of gradient or and derivative. So the gradient, so when you're, so I hope you still remember what's the definition of derivative. And gradient is just a vector of partial derivative. And again, just to make more concrete, in our example right here. So we have the JWB function, and there are actually two variables, which means when I'm taking, actually, it's not derivative anymore, it's only partial. I take partial derivative of this loss function versus the W. I take another partial derivative of this loss function versus the B. And together this builds a 2 times 1 vector. This is my gradient vector. Gradient is a vector, okay, to emphasize that concept. Again, so if you your variable is a p-dimensional vector, your gradient is also a p-dimensional vector. I hope this is clear, and this is extremely important. All right. Oh, I see, I already copied that here, so, okay. Yeah, so my gradient, yeah, let me copy the way I did that. Gradient of J, WB, and then versus, so let me summarize it as the theta, right? It's just a theta vector. Easier, make it easier. Is the partial derivative of J theta vector, oh, versus the first theta, like theta 0 in this case is B. Oh, actually, this is theta 1. And then theta 0. Here, theta is a vector. Sorry. Theta is a vector. It's a 2 times 1 vector, W and B. And just to make it more clear, theta 1 and theta 0. It's probably just write it into a matrix form. Okay. All right, so, okay, so why like optimize through gradient descent iteratively? Because it works on any objective function as long as we can evaluate the gradient. And this is very useful for minimizing complex functions. And most functions cannot do something we did in the normal equation case. We actually can solve that gradient equal to 0 equation. For many functions, you don't have a closed form solution by just using that constraint, set gradient to 0. All right, so now let's make it really concrete. What is the gradient descent to solve the super simple quadratic one-dimensional function. Again, so let's review what is derivative. So I actually put this derivative equation there, which is a little weird, but I hope this give you a little, remind you, I mean, how do we get the 2W? So the derivative, so what is derivative? Derivative is described as the instantaneous rate of change, the ratio of that change in the fx to the changes in the x. It's a little difficult to understand here, but so let's just make a very concrete example in the next page. So let's use gradient descent, that gradient descent equation, and then applied it here. So if you still remember that gradient descent equation is a equals to xk minus 1 minus alpha, I think is gradient x here. And then think about now my f function is the w quadratic minus 3. And then we replace this part by 2w, right? And this is actually k minus 1. Very important. It's the gradient of the derivative values at that xk plus 1. So we replace this part into 2w and that value at the k minus 1 epoch, which give us this wk equals to wk minus 1 minus 2 alpha wk minus 1. All right, I hope this explains. So let's look at this a little more concrete. Okay, so assuming I'm at the, this is not x, this is actually w, yeah. Yep. So when w equals to 2, what is its, what is the gradient? Yeah, I'm going to get this out because we already derived it. So when w equal to 2, so this is LW. I'm trying to, and for a specific point, wk minus 1 equals to, hopefully, equals to 2 L prime W at that point, k minus 1 equals to 2w k minus 1 equals to 4. All right, so what does this even mean here? So what, and let's see what wk is. Wk, what for, is 2 minus 2. Let's just put alpha equal to 1. Let's assume alpha equal to 1. 2 times 1, 1 is too large. Let me do 0.1 times 0.1 times 2. So what is wk? Is 2 minus 0.4, so which is 1.6. I think I'm correct. Yes. All right. So wk. So I'm wk minus 1 is 2, and then this gradient descent tells me to move to the left. And then multiply the step size is controlled by the alpha and also controlled by the gradient, which is 2wk minus 1. In this case, is 4. So it actually moved a slightly smaller step. It moved around about here. So it moved to is WK move to WK minus 1, move to WK. Okay, so it's a good move, in fact, right? So now let me actually emphasize we can actually think about gradient or the derivative directions. So I'm going to clean up everything here. So and make it like this W. So the 2W, one, it's the 2W in the end, this LW. So derivative and gradient actually pointed to the direction function increased the most. That's just a definition of derivative. Look at this equation. And this is, you move a little bit versus before. You move a little bit and the direction actually increased the function the most. So naturally, LW, when it's positive, it tells you at that point, if you want to make function larger, because that's at that point, the gradient just tells you what direction to make the function large, which is at the right direction. Because gradient and derivative tells me direction, what direction increase the function. And my goal now is to minimize my function, which means I should go the opposite direction of the gradient of the derivative. And this is why gradient descent makes sense. So let's come back to see that original equation is xk equals to x is from the previous xk minus 1 minus alpha, and the generic case xk minus 1. Okay, now let's still review this. Gradient tells me what? This gradient vector tells me at that xk minus 1 point, this is the direction that increase my function the most, because I want to minimize the function, not maximize the function. That's why I'm going to the opposite direction, which that's why there's a minus here. But when you go to the opposite direction, how much should you jump? And you multiply by this alpha, called learning rate, kind of control how much do you jump in the opposite direction. Question about this? This is extremely important. So okay, so no question. Okay, so then that's again, so gradient is the direction. So this is the gradient direction. And so let's go to the left side. Okay, so let's go this side. I mean, if my WK minus 1 equals to 3. And then what is the gradient at that direction at this point? Minus 3, actually not 3, minus 3. So this L prime at WK minus 1 here equals to minus 6. So it tells me actually go to the left. The more left I go, the more increase is my function LW. And as gradient descent, I should do the opposite way. Instead of going left, I should go right. So the gradient descent is to descent. It's the opposite of gradient. All right, so enough talk about gradient directions. Now our WK is 1.6. So what should be the WK plus 1 then? It's 1.6 minus 2 times 0.1 times like 1.6. Yes, that's actually true. Yes, that's actually true. So what does 1.6 minus 0.32, so I get 1.28. Yeah. So now I moved a little bit more again, so I moved a little bit more, map to this point, 1.28, which is my WK plus 1. I can just keep, on the surface, it's equivalent to, I'm doing this second step. So this is the K minus 1. This is the K. This is the K plus 1. And then again, and to hopefully converge very closely to the 0. And this is exactly the gradient descent is doing, just by keep updating your current W, the variables values based on the gradient. All right, so just a few concerns when you use gradient descent, and we will use our concrete examples to show you why they matter. The first is learning rate matters. Okay, so now let's start from omega 0 equals to 3, start from 3, and let's use a very small learning rate. 0.01, maybe 0.001. Okay, so what would I get as W1? Equals to 3 minus 2 times 0.001 times 3, which gives me, so in this case, like 0.006 gives me 9.994. All right, so just to show you, so this is like W0. It just goes very tiny. Yeah, it's actually more than 99 something. Really, it's a really tiny left move. So this is on the cost curve, and this is in the parameter space, in the W space. You go left a little, only just a little. All right, so now let's use a different learning rate. So this gives, it's like, let me don't use this, make 2, like 1.2 times 3, yeah, to like 6. This is minus 6, minus 4.2. All right, so this is minus 4.2. So I start from 3. This is just exaggerating really big, and I go to, wow, minus like 4.2, minus 4.2, which actually you can tell that f value is, let's see, fw0, or maybe lw0 is w quadratic is 3 quadratic minus 3, and this lw1 is minus 4.2 quadratic minus 3, which is actually even larger than the L0, omega 0. So which means we actually got not minimize, not making it smaller, actually make it larger, so which is bad. And then the second is the objective function matters. So this I'm trying to show you, like, there are 2 different functions, and first is the 2x quadratic, the other is x quadratic. So it's actually easy to tell, right? This function's gradient is 4x. And this function's derivative, because there's only one variable, is 2x. So apparently, if you start from the same starting point and same like learning rate, and so look at this, they all both start from x0, and then for this green, like more flatter function, x quadratic, it moves to a little bit left is 2.4. It's actually, they all start from 3, right? So from 3, so this is they all start from 3, and then on this a little flatter function, it moves only 0.6, I mean, to the left. But on that function more steep, like 2x quadratic function, it moves much faster. It moves from x0 equal to 3 into the position 1.8. So what I want to show here is objective function matters. And then the last, it's what I want to show is starting point also matters. So which I try to give you a more concrete, and here is a more exaggerated version, is the small, so there, you really want to keep yourself on the good side, but not on the kind of plateau side. So the plateau side, because it moves really, really slow, I mean, because just the gradient is small, I mean, it's very, very small. And then you want to keep the alpha to be small if your starting point is here. So assuming you start from a good side, then try to control the alpha learning rate to help yourself stay in the good side. Because if you go to the bad side, you will stuck there pretty far long time, just because the gradient is so small, it's harder to jump out from the bad side. So even more exaggerated, so like this, the left is very flatter, it's 1/100, and right is for x quadratic. So this issue actually related to 2 points. First is starting point, second is learning rate. So it's not just only about starting point, it's about both. So you want yourself hopefully start from the good side and also have good learning rate. So we don't want to jump from the good to the bad. So comments, so last, it just to summarize. So comments on gradient descent algorithm, it works on any objective function, and as long as we can evaluate the gradient, and this can be very useful for minimized complex functions. And but the issue is it can have multiple local minima, and but for our linear regression, because there's only one single global minima, so using gradient descent, there's no problem. We don't need to worry about it. And if you worry about your function is too complex, gradient descent goes to the closest local minima. So you can use some like random starts, or there are many, many other initialization techniques, especially in the deep learning research, to help you start from a good side. Yeah, that's it.